we will have the honor to hear Dr. Harshman talking on symmetry, solvability, and emergent subsystems.
All right. Well, thank you. First off, thanks to the organizers and to all the people who helped make this possible. This is my first trip to Buenos Aires, and I'm very happy to be here. And I'm very happy to be speaking to such a crowd of diverse interests, interdisciplinary interests. It's very exciting. My title overpromises because I had hoped when I wrote my title that I would have some grand unifying statement that would solve all the problems. But instead, I'm going to stay in my comfort zone and present you things I know. So I apologize for that because the known ends up being probably a little more technical than I would have wanted. But I think it'll be a fine balance. OK, enough apologies. OK, but first, again, since I don't know very many of you, let me just say a few words about who I am to establish authority. So I was trained as a theoretical particle physicist. Studied with Arno Bohm the phenomenology of resonances and decaying states, and was very interested in relativistic quantum mechanics to differentiate to some degree from relativistic quantum field theory, but relativistic quantum mechanics. It was my interest in relativistic quantum mechanics. In the early 2000s, people started talking about relativistic quantum information theory. So I actually got into quantum information theory from that back door. And then started thinking about the relativity of entanglement. There were a lot of questions about what kinds of entanglement are relativistic invariants. And so then that sort of got me thinking about entanglement as a mathematical, the mathematical structures required to define entanglement. And in particular, I've always been interested in trying to use quantum information theory to think about entanglement in interacting particle systems. So not qubits, not necessarily with applications to quantum computing, but to see what quantum information can tell us about some of the hardest problems, right? Interacting particle systems, nuclei, atoms and cold atom traps. And so that's actually what led me to my most recent sort of change of season. I've been spending the last few years really thinking about these topics in the context of few body physics. I just got done with a sabbatical in Aarhus, Denmark, where I was visiting Nikolai Zinner and his few body physics group, theory group. And what led me to this is when I started to try to understand quantum information theory applied to particles. Again, I started really thinking about the power of symmetry. And the big idea in few body physics is we know that if we have a two-body system, it is always solvable and integrable, at least in some sense. If we have an isolated two-body system, that's been known since Newton or Lagrange or something. But as soon as we get to three bodies, Poincare showed that the general three-body problem is not integrable or solvable necessarily. There's some distinctions there. So then that really got me thinking about few-body physics as the sort of the ragged edge of integrability and what interesting physics there. I would claim that a lot of times when we talk about quantum physics, we use examples of integrable systems. And as a result, some of our intuitions come from that. And maybe I'm interested in systems that we don't have that much mathematical power over. Yeah, so I've been thinking about integrability, controllability, and chaos. OK, and trying to use some of these ideas of quantum information theory to talk about that. My favorite kind of mathematical physics, right, is regular polytopes. And not just because they're pretty, but because they're classified. They're classified in every dimension. They're classified forever and for all times, right? And so this is something that's very appealing to me. And of course, their organizational system, right, the classification system of regular polytopes actually turns out to be relevant to classifying space groups and kaleidoscopes and matrix groups and Lie groups. They're not all the same, right? But all of these dynamical phenomena, some of which are of current interest, like topological insulators and superconductors, all the way through, again, the basics of geometry, they all have a related classification system. And this is the kind of structure that maybe you find one of these structures and you say to yourself, oh, well, I don't find a natural system that has this. But then eventually, sometimes you do, right? You find the buckyball, and suddenly it says, oh, there really is icosahedral symmetry in nature. So now, I showed this slide, and I want to give the caveat, but I do know symmetry is not everything. I don't believe that everything can be turned into a kinematic theory with symmetry at the root. I don't think that's going to be enough, and in lots of contexts, there's lots of no-go theorems that says you can't do it, but I'm really interested in the edge of what it can do. I also want to say I'm not some sort of naive Platonist. I know that when you put up that, some philosopher is going to say I'm some sort of naive Platonist. I'm not naive. All right. I might be a Platonist, but anyway, okay. So I'm going to talk about what maybe sounds a little dry, but I'm going to talk about structures in the Hilbert space structures, because again, I'm interested in deducing structures, right? And so I'm going to be talking about sums of Hilbert spaces, and I'm going to be talking, and so I'll talk about some of these things, but right, both the ways that sum of Hilbert spaces naturally arrive in a quantum theory, and also some of the applications of sums of Hilbert spaces where they come up. So I'm going to talk about some of these things. I'll talk about products, right? And there's sort of a whole host of related topics, many of which are of interest to people well, especially to Olympia Lombardi's group, right? This is sort of, I think, why I'm here is because I'm interested in this observable induced subsystems and things like that. And of course, what we really want is combinations of both. That's going to sort of be an underlying theme, right? Is that when you have a model of a quantum system, and the more ways you can break them into sums and products, the more mathematical power you have over the system, the more likely it is going to be controllable, integrable, and solvable. I'm going to talk about Hilbert spaces and pure states today, but I am not a fetishist about either one. Most of this stuff can be extended to more general contexts. And in fact, I mean, we know that there's lots of things that are difficult to talk about in the Hilbert space, and you either have to go to a subspace or that it's dual. But I'm not going to worry about that today, and I'm not going to try to make every statement general enough to cover density matrices. Okay. So what are my motivations? Well, so again, I'm a mathematical physicist, but I still would say I'm a physicist first, and so I have been working for the last few years a lot in few-body physics with cold atoms, and I'm going to ask you to indulge me to talk a little bit about that physical system, just so we have a nice context. But that's one of my motivations, right, is this is a physical system. There are people who can there's a group in Heidelberg that can put 7 atoms in a cigar-shaped well of light that's effectively one-dimensional, and maybe they're spin 1/2 systems, and they can literally say, I want 3 up and 5 down, now let's look at the dynamics, right? So they're really doing these few body dynamics in labs right now, and in particular, 1 dimension, symmetry is more powerful than in 2 and 3 dimensions, so that's where I'm studying. Right, and of course, one application of this, right, is for quantum information technologies. If we study these systems and we end up finding the right ways to break them into subsystems, sometimes those subsystems have the right properties for preserving or processing quantum information. But I have also the sort of the other side, right, the sort of the intellectual inquiry is, so a lot of people are using a lot of different mathematical techniques to sort of solve these models and to study these models, to study the physics of these models. And the question is can we use ideas from quantum information theory and from these kinds of Hilbert space structures to add new physical insights here? Not just to sort of give applications, but to actually apply it to them and see if we can get something new out of it. Because I would argue that hasn't yet had its breakthrough moment, but maybe I'm too cynical. And there's some other motivation that I have trouble putting into words, and one of the reasons I'm glad to be here this week is I'm hoping that in this conversation I will learn the words to say what this something else is. But let me talk just a little bit about this particular physical model. Right, so it's particles moving in 1 dimension. They are all trapped in some trapping potential, so it really is a discrete energy levels. And then this is the simplest sort of interaction. It's a right, I only have 1 scale parameter in this interaction, so this is a contact interaction. So they literally only feel each other. If this was a classical model, they only feel each other when they're actually hitting. That coupling strength G, or that interaction parameter G, if you take G all the way to infinity, then this is the quantum version of Newton's cradle, right, of the balls just hanging there and bouncing off each other. So that's the physical perspective of this. Right? If G is not infinity, well, then the balls can pass through each other, right? But so this model, when G goes to infinity, is integrable. And because it's integrable, it thermalizes really slowly. It has lots of very interesting properties. It's interesting to control. Yeah, and again, to actually study a real experiment, you have to embellish the model. Maybe you take into account that they're actually indistinguishable particles. You have to worry about that kind of symmetrization. Maybe the particles have internal structure or spin. Maybe it's not homogeneous, right? Maybe they're different mass particles and different coupling constants and different traps. You could consider more general two-body interactions. Maybe you have some finite range. Maybe it depends on the internal structure. You could add in intrinsic few-body interactions. Or anyway, you could do all sorts of stuff. And they're actually, again, they're doing these in the lab. And so that's what makes this exciting. So I just want to sort of say, again, part of the maybe academic questions that I'm interested in is there's actually a whole range of one-dimensional few-body models that have a long history in mathematical physics. And it's not always clear how these are all different and how they're related and how they're how to categorize and relate these, how some of them are limits of other ones and not. And so part of the reason that I'm studying this is I like to classify things like the Platonic solids, right? So partially I'm trying to make sure that I understand what is the web of connections of all these different models. My fantasy, right, is you give me a model and I can make a meta-theoretical judgment about its solvability, about some of its properties, without actually needing to know everything about the model itself, about the details of the spectrum and the states. The particular model I'm interested in, again, I'll throw some of these words around and I'm not even going to define them. I'm just going to say, but these are the kinds of physical issues that I'm interested in. Integrability, and there's sort of different subclasses of integrability. Again, loosely speaking, integrability is when you have as many conserved quantities as you have degrees of freedom. That's loosely speaking, but that's a reasonable handle to put on it. I'm also interested in the question of separable. And I mean separable here not in the context of either separable Hilbert spaces or necessarily in the context of separability in entanglement and all that, but the notion of separable in terms of can you separate the degrees of freedom. And again, there's different degrees there. Sort of weakening down, I'm interested, sometimes you have a problem that's analytically solvable without being integrable or separable, but again, there's exactly solvable in terms of algebraic expressions, and then there's maybe just constructible. You can get a solution of arbitrary precision in a finite amount of time, right? So there's a hierarchy here, and then we can even go all the way down to numerically solvable, and what kinds of powers we have to, is the problem even well posed? Will a small variation in the control parameter lead to wild variations in the outcomes? And that's a different question than chaos, which is its own black cloud hovering over the whole thing, right? And we know there's also a hierarchy there and interesting questions. And then again, finally, what does this all have to do with information? Okay, so again, I'm not going to answer any of these questions. I'm just trying to introduce to you the vocabulary that I'm interested in. Okay. So yeah, so again, I claim that this model actually has it all depending on the number of particles, the actual shape of the potential, and the strengths of the interaction. Is that almost all of those different categories that I put up before, I can come up with a specific model that has that property, but not that property and this property, right? So it is, and again, this is a little bit of an advertisement. They're doing this in the laboratory. So I think this is a very fertile place that if you're interested in foundations of quantum mechanics, particularly these kinds of dynamical issues, the foundations of quantum mechanics, this is a really interesting system to study. So yeah, so you can actually do these experiments, tunable systems with discrete and continuous degrees of freedom that interact with each other. There are possibilities for finding topologically protected sectors. One of the projects I'm also working on is, for example, in these systems, you can embed combinatorial problems that are really hard to solve, that scale very unfavorably, but in principle, if you could embody them in a quantum system, you could get some sort of linear, or maybe I shouldn't say, you can get a better scaling of solving the problem. And then sort of more of the topics here, maybe more the connection to some of the topics we're talking about here, the idea of emergent subsystems as a framework to thinking about the preferred context to study these things, and how is there a preferred context, and is it different if it's an integrable system or a chaotic system? And then there's something else. Well, so maybe for the sake of intellectual honesty, I'll also just mention, if I'm going to focus so much on solvable, what do I actually mean by unsolvable? I mean, is there some sort of opposition? So right, I could just mean unfavorable scaling. I have some deterministic algorithm that would get me to a solution, but there's not enough matter in the universe to build a computer big enough to solve it in finite time or something, right? There's just bad scaling. It could be, right, I have uncontrollable errors. Like, we know that if I'm talking about a molecule or a nuclei, those parameters that determine the interactions those appear to be fixed in the universe now and for all time. So I'm talking about those systems maybe where those control parameters really are variable. And so we want to understand there may be systems that we study where those errors aren't controllable, where a small variation in parameters leads to wild variation. Even high order polynomials, right? That's, if you have a large order polynomial, the roots are ill-conditioned on the coefficients in the polynomial. So this is a real mathematical issue. Then there's maybe, another possible meaning of unsolvable is that I'm asking the wrong question. I'm asking for some sort of incompatible observables and to try to get meaning out of that. So that could be just an ill-formed question. I could be asking good questions, but for an ill-formed model. In other words, the model doesn't have the realm of physical applicability that I thought it did. I could be talking about an ill-formed reality. I sort of tease sometimes that this is what I worry about social science, right? Social science is such a complex system that reality is too complex for us to say anything meaningful about. That's an unsolvable problem. Can't disentangle things. And then finally, it really could be ill-formed mathematics, sort of like the conversation this morning. For example, there's another famous problem by a guy named Tony Cubitt. There's a model of a solid state model where the question whether the ground state is gapped, and this is a big issue in solid state mechanics, if the ground state is gapped, to answer whether the ground state is gapped for this model, you have to, it turns out is equivalent to deciding the axiom of choice. Right? So it really could be that some of our physical models are really, this is a model that has infinity in it, and so maybe the problem is that I shouldn't be talking about infinity, but the point is we could have ill-formed mathematics. So I'm really mostly, oops, the box didn't get it, but I'm really mostly talking about the first two today, but I wanted to just sort of say I'm interested in solvability, and this is the opposite. Okay, now I'm going to start doing, I'm going to get down to business. How am I doing on time? Does anybody know? I've gone 20 minutes, or I have 20? Oh. Nice, okay. Yeah, so I'm going to talk, I want to talk about Hilbert space arithmetic. I actually think this is, again, this is in the spirit of, I want to try to classify what are the logical, or at least the mathematical possibilities of quantum systems, right? So certainly one thing I can do with the Hilbert space is I can break it into orthogonal subspaces, a direct sum of orthogonal subspaces. Let's just start with some examples, right? And again, many of you either will know all of this entirely, and some of you will know none of this. So I'll shoot right down the middle, so everybody's either bored or lost, okay? I prefer to give a meta talk than a talk, if possible. Okay, so we have the spectrum of the Hamiltonian, right? So we have a decomposition of the Hilbert space into energy eigenspaces. This is the classic one. And if you have a closed system, this is of natural interest because we know that the Hamiltonian is going to tell us how this system evolves in time, right? We know that each space is going to carry a nearly trivial representation of time translations, just a phase. They won't all wind at the same rate, and there are obviously very interesting effects there. If you don't start in an energy eigenspace, you can get interesting interference effects. If you start in one, it's basically trivial. And then there's lots of interesting questions here, right? We could talk about if I change my Hamiltonian, what happens to these spaces, right? And this is classical, spectrum physics, right? Do these spaces split? Do they split discontinuously? Do they split gradually? What if I do adiabatic changes? What if I do rapid changes? What if I drive it periodically? Like all of these are obviously interesting physical questions that can be framed in terms of what happens to the energy eigenspaces as I change parameters of my model or open my model up. Okay, of course we can generalize this to other observables, right? If I have some single observable capital lambda, and if it has, and by observable I'll assume it has all the properties necessary to have a spectrum, and then I can and a decomposition of the Hilbert space. I could have commuting observables, right? Now generally, so here that's supposed to be a bold lambda. Now generally my bold lambda is some set of parameters that's going to characterize the spectrum of my commuting observables. But it could be that my spectrum depends on the observables. The same way, right, you can't just have any m. You have to have an m that ranges between L and minus L, right? So there's some relationship between the eigenvalues. The spectrum of eigenvalues is not independent of what the other observables are. So you have to sort of think about the joint spectrum of all of these observables. But there are some systems where you have what I'm trying to rename golden separability, right? Where in fact, you really do have an independence of the spectrum of each one, right? So an example of this might be something like the harmonic oscillator or the isotopic harmonic oscillator in any dimensions, right? You can break it into independent quantum numbers for every mode, right? That's a case of golden separability. Hydrogen atom, over there. What else is over there? Lots of stuff is over there. Some things are over there. Right? This is definitely that's one thing we really mean by separability, right? If you have a totally separable differential equation and the separation constants don't depend on each other, right? You have independent separation constants. That's what I mean there. And of course, the even better than golden separability is when you have golden separability and you have a complete set of commuting observables. So each one of these spaces for a given lambda is just a complex number, right? And if you normalize it, right, just a phase. Okay, so that's your dream case. Okay, so what I want to do then, right, is so where do these observables come from? Well, we know one place these observables come from is for continuous symmetries. They could be the generators. Or even for discrete symmetries, they could be some Hermitian combination, some representation of those symmetries that is a Hermitian operator and therefore also an observable. So I just want to say a few things. I'm going to talk about the relation of symmetry to this, but I just want to sort of remind you the types of symmetries, and in particular the types of symmetries that I'm interested in few-body physics, right? So I could be talking about the symmetries of space itself. I could be talking about symmetries in configuration space, right? I can think about particle permutation, the permutation of identical particles, as a discrete symmetry in configuration space, sort of a geometrical embodiment of it. And I find that very useful for solving problems, both for intuition, but also it connects you to a literature of math that's very useful. You can do the same thing with phase space. And then you could even go all the way up to the Hilbert space. You could talk about, right, so all the first three, right, maybe symmetries of actual spaces that then I lift to a representation on the Hilbert space. But you could just talk about symmetries right on the Hilbert space, just maps between different subspaces like that. And again, all of these different symmetries can have all sorts of different flavors, different kinds of, I'll say more about kinematic and dynamic. I won't say anything about algebraic or topological, which is a bit of an idiosyncratic definition anyway. So but they could be exact. They could be linear symmetries or nonlinear symmetries. They could be local or global. They could be reducible to one part. If you're talking about few-body physics, they could be reducible to one-particle systems, to product of one-particle systems, or they could be emergent. They could only come when you have the combination of them. And then again, the actual structures of the group tell you a lot about how these structures are then represented on the Hilbert space and how they could be used to break the Hilbert space into subspaces. So that's just sort of making sure the context of the power of symmetry is there. Probably not necessary for, I don't know. Yeah, so then the idea, right, is you can use one way to take a Hilbert space and break into orthogonal complements, orthogonal subspaces, is, besides observables, is to actually use the symmetries themselves, right? The simplest example is parity, right? If I just have parity, then I can always break my Hilbert space into plus and minus parity states. I'm not even saying that my parity commutes with my Hamiltonian, right? If parity commutes with my Hamiltonian, then each of these are dynamically decoupled. But even if it isn't a symmetry, like I can still break my Hilbert space up like that by imposing some sort of representation of parity. More generally, what this is a special case of is if I have a symmetry group, right, I can come with the unitary irreducible representations of that group, the IREPs for short, and then my Hilbert space will break into subspaces. And each of these subspaces are sometimes called a symmetry sector or sometimes called a tower, right? So those are all that part of the subspace that has, it might be all the positive parity states, or it might be all the L equals 3 states. And there's an infinite tower of these states, right? And the tower, then, is the direct sum of the actual irreducible representation spaces, right? So I mean, this is all known quantum mechanics since the time of Weil and Wigner, but just to sort of give my notation out here, right? So give me a symmetry, and I can break it sort of into this double sum. First into a tower, and then I can break the tower. I have to come up with some sort of, I have to come up with some sort of index here, right? And that index, choosing that index in a sensible way, that might be a hard problem. It might even be an unsolvable problem, but in principle, I have something like this, or it might be an arbitrary choice. But okay, so then again, especially if I'm interested in closed systems, maybe I want to, well, so let's talk about the relationship with the Hamiltonian. Yeah, so I have this one decomposition, and then I have the decomposition that symmetry gives me. And so then I'm going to break my symmetries into two categories. The kinematic symmetry, so I'm using the terminology of Dirac from like a 1949 paper where he classifies relativistic, the relativistic dynamics in quantum mechanics. Actually, I think he may have even been doing classical. But so the kinematic symmetry group is going to be the group of, I'm going to call it a kinematic symmetry group if that symmetry group is a symmetry of the Hamiltonian, right? And so what that means then is that I can take every energy eigenspace and break it into some sum of representation spaces of my group. So it might be like the hydrogen atom. I'm talking about the second, not the ground state, the second excited state, right? And so this could be some sort of sum of different L's and different M's. If I have identified the maximal kinematic symmetry group, if I've squeezed all of the symmetry out of the system, and that's always what I'm trying to do, then I can find a symmetry so that every single energy eigenspace is exactly one irreducible representation of the maximal kinematic symmetry group, right? Then you've really squeezed almost all the symmetry out of the system, at least all the kinematic symmetry. Just to sort of extend one more step, if I have a dynamical symmetry group, you can think about it the other way. What that means is I have some symmetry that may not commute with my Hamiltonian, but it still maps energy eigenstates into other energy eigenstates. It can act like a ladder that connects states of different energy, right? And so that's sort of the reverse of this. Instead of decomposing my energy eigenspace into irreducible representations of my kinematic symmetry group, if I have a dynamical symmetry group, my irreducible representations of that big symmetry, that's a tower of different energy spaces. Maybe not all of them, maybe just some subset. But so that's sort of the reverse side of this. So I recognize this is all sort of a little bit technical, but the main story here, right, is that symmetry gives you a way, lots of ways, lots of complementary ways of breaking your system into subspaces, right? And the claim is these are the subspaces then will be distinguished by measurements, right? This is where the information is going to be stored and extracted from. And so caveat, yeah. So again, I said this is inspired by Dirac. If you read the literature, people use the term kinematic and dynamic symmetry in lots and lots of different ways. And so I just want to say that as a caution. And then finally, this is not a well-defined notion. It is a circular definition, and I'm totally aware of this, right? I'm saying I found the maximal kinematic symmetry group if I have found the maximal kinematic symmetry group. So that's a little bit of that's weak sauce. Okay. In particular, if we're going to talk about identical particles, right? So without even assuming anything about how my system is built out of these particles, I'm just going to say if I have a Hilbert space that's supposed to represent two identical particles, I can always break it. I can always break it into the symmetric part, the part that's symmetric under the exchange of the particles, and the part that's anti-symmetric, right? I don't need to know any more physics than to say if there's this symmetry, this decomposition is meaningful. And if I go to 3, now I have 3 spaces. The symmetric. I'm using sort of Young tableau notation. I don't know if this notation is familiar, but this is sort of like 3 boxes all in a row. And so this means it is symmetric. This is 3 boxes in a stack. That's anti-symmetric. And this is a subspace of mixed symmetry. And then we go to 4 particles. And we now have 5 spaces. And generally, this number grows grows fast. I should have looked at it. I can't remember what it is. But as this gets up more, the number of these subspaces grows fast. But often, if we're talking about identical particles, and meaning truly identical particles, and that maybe they had some sort of internal degrees of freedom, but we've already taken that into account, then we're usually only interested in either the totally symmetric spaces or the totally anti-symmetric spaces. And so is this what you meant by Decio? Is this what you meant by the symmetry trick? Didn't you call this a trick, right? Because in other words, I'm going to solve the problem, and this is what I always do, right? Is I'm always going to solve the problem assuming that they are distinguishable particles, or at least not everybody does it this way, right? There are other approaches, especially in quantum field theory. But in few-body physics, I typically solve the problem as though they were distinguishable, but identical, and then I pick the states I want. There's some extra overhead doing it this way, but it turns out then there's always some other degree of freedom that you forgot that ends up making these other spaces relevant, because suddenly it turns out, oh, it's not really one-dimensional, it's two-dimensional, and we have to start adding in these other degrees of freedom. So, okay. So yeah, so there's identical particles, and that's the end of, yeah, so I'll come back to that later after I've talked about products, okay? So I think the last section was the most technical section. I don't know why I keep apologizing for that. It's the part I actually love the best, but you know, we hurt the ones we love. So I want to talk about products, right? And so when I think, and maybe I'm naive, when I think of a subsystem, what I'm typically thinking of is I'm taking my total system and breaking it into a tensor product. And that's almost, again, that's my definition of what I mean by a quantum subsystem. So I want to, again, sort of talk about how do you get quantum subsystems, right? So, of course, the most straightforward is I have a quantum system here, and I have a quantum system in a vat in Antares or whatever, right? I have all of these totally disconnected, non-interacting systems, and my total system is just the direct product of all of those, or the tensor product of all of those. What I'm often working with, right, are interacting systems, and I make the assumption, and it is an assumption, right, that the total Hilbert space for my interacting system can be expressed as the tensor product of my non-interacting systems, right? That those two spaces are isomorphic, that there's a one-to-one map. That's not always true, and we know that's not always true, and there's lots of cases where that sort of breaks down because it turns out there are states that you can't describe this way, right? And there's a whole story there, and it's even worse when you're dealing with Fock spaces and quantum field theory. But the way maybe I'll talk most of the rest of this section on is virtual subsystems. And really virtual subsystems or observable-induced subsystems or maybe measurement-induced subsystems or decoherence-induced subsystems. These aren't all the same things, but to me, they all come from some sort of algebraic approach, right? An algebraic approach thinking about what observables are real, or no, what are meaningful, are the preferred context, is that the right word, right? And then trying to break up my Hilbert space into subsystems using those. Yeah, and then and maybe a particular example of that is if you're talking about systems and environments, system and environments, yeah. So I call this Artiste Theorem. I don't think everybody calls it Artiste Theorem, but when I understood it for the first time, I felt like I had to celebrate it by naming it after the author. I don't think it's caught on yet, but so what do I mean by Artiste Theorem? Oh, well, so first let me just give the example, and this is a standard example, and I've read it in several of your papers too, so this is standard. So let's say I've got a Hilbert space, so a finite dimensional Hilbert space realized by complex 4 tuples of numbers, right? Well, of course, one natural way is that we could think of this as this is the Hilbert space that I get when I have 2 qubits, right? Alice's qubit, and the algebra of Alice is just the span, the algebraic span of Alice doing something on her own qubit and nothing on Bob's, etc. Here is Bob's algebra of observables, and this is the algebra of observables that corresponds to our natural sort of decomposition of our 2-qubit Hilbert space into Alice's qubit and Bob's qubit, right? And by this tensor product structure, we have a notion of separability, where these are all the separable states, and then these are a selection of maximally entangled states, right? So we have this natural, again, we have a natural decomposition here. But at least the first place I read it was in Zanardi's paper. let's choose another. So this is an isomorphic repartition of the algebra of observables. P is isomorphic to A and Q to B. They're commuting. They commute with each other. Their product spans the whole space of observables just like it should. And in fact, yeah, and they both are the enveloping algebra for SU2, right? So this is equivalent in every way. And it gives us a new partition of our Hilbert space into Prentices and Quentins, virtual qubits, right? And in this particular repartition, these states, now expressed again back in Alice and Bob's basis, these are the separable states, and these are the maximally entangled states, right? So this is the classic example of the relativity of entanglement. Yeah, and so Zanardi just sort of formalized this. Again, I would claim it's only for finite dimensional Hilbert spaces. Right, so you get given a state space, and maybe you should be careful and take a dense subset of the Hilbert space. I won't worry about that now. And a collection of subalgebras of the total operator algebra acting on the Hilbert space. The subalgebras induce a tensor product structure if they satisfy the following. There are two mathematical criteria, subsystem independence, and then completeness. Right, the subalgebras commute, but the combination of the subalgebras yields the whole algebra. And then he gives one physical criteria that he calls local accessibility. Each subalgebra corresponds to a set of controllable observables. That's an opinion. No, I mean, right? I mean, so this is right. So this is either the crux or the weakness or something, right? But this is the important part. So I'll change the font color. Yeah. So this is what I am really interested in, and it was when I read this paper that I understood what the problem was with all the works I was reading in relativistic quantum information theory, is because they weren't talking about the same partition of degrees of freedom. They were comparing different tensor product structures and talking about which ones were invariant under relativistic transformations and which ones weren't, and they were getting into fights because they were talking about different tensor product structures. And it was finally Zanardi that gave me the language to talk about how am I going to partition my degrees of freedom in a way that is sensitive to the symmetries of the system. So let me just say, I have to advertise myself again. This is my slight extension of Zanardi's theorem, which really just says that if you have a Hilbert space of any finite dimension, you can always, it's a finite construction. There's a finite construction of observables that will allow you to repartition this Hilbert space in any way you want to, as long as the dimensions multiply to the right total dimension. Right? So it really says that prime dimension Hilbert spaces are different, right? That's one consequence. And really the whole proof is just basically saying that all Hilbert spaces with the same dimension are unitarily equivalent. I mean, it's not really a dense mathematical theorem. Yeah, let me say, this is for pure states. It is certainly not true for mixed states, right? The totally mixed state is the totally mixed state under any partition. And I would claim that this is not proved for continuous variables. I think there's real issues going there, and I think they're interesting issues, but I've never been able to solve that problem. Yeah. So then the question is, right? So there's this relativity of entanglement, this relativity of tensor product structures. So sometimes when I've given this talk, this leads the audience to believe that therefore entanglement doesn't mean anything, right? Or somehow this undermines the whole game, right? If everything is equal, it can be changed into anything else. But no, there are other physics that we have to worry about. There's, again, maybe a preferred context. And so I'll say there are reasons that certain tensor product structures emerge as the physically meaningful ones. Right? So in sort of Zanardi's original application, he was thinking about decoherence-free subspaces and superdense coding, and so he really was trying to think about what kind of control, what kind of input, what kind of output were we going to use to, and so maybe we shouldn't be using the qubits, maybe we should be using some sort of superstructure of qubits repartitioned. Maybe you have a decoherence mechanism, either closed or environment-induced, that selects certain partitions as more stable or more physical or better able to maintain their coherence. The two that I'm going to talk about are a little bit, I still have a few minutes left? I'm almost at the end. Yeah, okay, I'm almost there. Right, and so of course, a natural way is that the separability that you get from notions of symmetry and separating partial differential equations when you solve the Schrodinger equation, that notion of separable sometimes does carry on, right, into tensor product structures, and you can carry that notion of separable over. And more generally, symmetry sometimes selects, or symmetry can select invariant subsystem partitions. It can say this partition is going to be the same in every reference frame, and therefore this is a useful kind of entanglement, or this is a useful way to quantify the correlations between these subsystems, because it is invariant under reference frame transformation. Yeah, so I'm talking about those two. So right, I had that case of golden separability before. Well, when you have golden separability, then each degree of freedom really can define its own Hilbert space. And again, as long as you have this kind of spectral independence, well then golden separability just naturally carries over into this kind of separability, right? It gives you a new sense of local, where local is defined by each degree of freedom. More generally, if you have some separable degrees of freedom, like for example, where I started was thinking about momentum and spin, right? You can talk about the intra-particle entanglement, the entanglement between the momentum and the spin of a particle, and you can think of a Stern-Gerlach device. The whole point of a Stern-Gerlach device is to generate that entanglement so that then the momentum points back to the spin you wanted, right? Or you could talk about scattering experiments, and an interesting consequence of Galilean or even Poincare invariants is that, right, you can separate out the center of mass degrees of freedom. Well, so that's what that really says is, right, that Galilean invariance or Poincare invariance really says that you can always separate your Hilbert space into a product for the internal degrees of freedom, which are not relative to the coordinate system, and then your external, which are. And what's even more interesting, and maybe I say it on the next slide, sort of, is that, right, this kind of entanglement is dynamically invariant. Right? Nothing changes this kind of entanglement. Generally, your initial state is generally highly entangled between internal and external degrees of freedom, then it stays highly entangled all through the experiment. The interparticle entanglement, of course, changes dramatically. That tensor product structure is not dynamically invariant. Yeah, so symmetry invariant, I've already started saying this, right? So for example, this tensor product structure is invariant under Galilean transformations, but not Poincare transformations. Poincare transformations do not factorize onto a momentum local and spin local unitary operator. The locality defined by this tensor product structure is violated by a general coordinate transformation. Maybe not everybody likes it when I use the word local that way, but I did it anyway. Yeah, and again, this one is invariant under time translations, if you're talking about scattering particles. And generally, there's some content here that's different from separability because there are integrable systems that are not separable. And that's, for example, a famous example are any model that is solvable by something called the beta ansatz. Those models they have as many degrees of, they have as many conserved quantities as degrees of freedom, but there's no way to separate that Schrodinger equation in any clever coordinate transformation you can prove. But you still, because it's an integrable system, you can still build a tensor product like this out of its different degrees of freedom. And so my final sort of claim is that what you want is to find as many of these as possible, right? If your system has multiple reductions into different sums and multiple reductions into tensor product structures, some of which are even symmetry, like maybe the same symmetry that generates this also is invariant this, then you've got a really solvable system. You've got a really controllable system. You've got a system that you can shift around the entanglement by choosing the observables that are interesting to you. Also, sort of related to this, right, getting back to the idea of classification, I'm interested in finite dimensional Hilbert spaces, right? And so you can enumerate the possibilities here. And so this is really something you can sort of think about. What are the kernels or the atoms of possible arrangements of Hilbert spaces of finite dimension, and imagine just enumerating the possibilities and looking for these manifestations. And I think that's an interesting project, and I think you'll find something. Yeah, so up to a unitary equivalence, there's only a finite number of symmetries. Also, the symmetry part, there's only a finite number of ways you could represent a symmetry, of symmetries that have a a unitarily inequivalent representation on a finite dimensional Hilbert space. So in other words, there's some interesting counting problems here. Just because they're finite doesn't mean it's trivial. And there are possibilities here that can't be built out of qubits, right? So that there are new things here. Finally, to get back to identical particles, right? What you sort of want, right, is one of the problems, for example, with talking about entanglement of identical particles, is that because you're talking about either the symmetrized or the anti-symmetrized sector, you don't necessarily have some sort of tensor product structure that goes along with this to naturally define. You can't use the particle tensor product structure to define entanglement because every state's, or for fermions, every state's maximally entangled by that tensor product structure. But if you have, when you have something that's very, well, what I'd like to understand is when can you do this? Because I say, again, this kind of system is going to be very controllable, very solvable, very interesting. Another interesting sort of set of questions here is what happens with the dimension of the irreducible representation. I've gone on too long. I'll just say if the irreducible representation is 5 dimensions or longer, algebra 5 dimensions or larger, algebra stops working the same way, right? For the same reason the quintic equation isn't solvable, all shit breaks loose. And so, yeah, so 5 really is different in my field, right? Understanding the transition from few to many is a big theoretical question. And so I say 5. That's my vote. That's when you go from few to many. So what are my conclusions? The arithmetic decomposition of Hilbert spaces into sums and products of subspaces is an underlying structure of quantum mechanics. It's denumerable, it's countable, it has a rich structure, as rich as the algebraic structure that gives us Platonic solids and Lie algebras and Lie groups. And symmetries induce structures in 2 ways, either by defining relevant summable units or identifying invariant tensor product structures. So they give a mechanism for emergent subsystems. I'm not saying it's the only mechanism, but they give a mechanism that I think is powerful. Something. And finally, few body physics is almost at the point where this amazing breakthrough that has not yet been come up with could have fundamental and practical consequences. So I think that's it. Again, thank you to the organizers, and thanks for listening, and thanks for staying awake after lunch.
Questions?
Oh, thank you. I'm not sure I need this. I'm feeling somewhat intimidated now. The camera's probably going to do as well. Can you go back to the slide where you had the same states being both maximally entangled and not entangled?
Right.
So, I mean, you alluded to this at the end where you said, like, so this is going to be a bit of a roundabout question. Okay?
That's fine. Good.
I'll just work my way up to it. So, at the end, you said, we can't, naively, you just say entangled means not a product state, right? And then because the antisymmetric sector doesn't overlap at all with the product space sector, every fermionic state comes out as entangled by that definition. That's obviously no good, right? But
at least as a resource definition, right?
Well, okay, right. So that's what I'm coming to. So, but then one could say something like, well, what we're really interested in is something like not a product state, not that some particular degree of freedom is not in a product state, right? If that's the case, then we're going to get Bell inequalities that will be violated by those entangled states if we just make measurements on that degree of freedom.
Right.
So what I didn't understand was how this distinction, if we think about the, and related to that is this idea of information theory that entanglement is conserved under local operations and classical communication, which again makes it seem like it's something physical, it's something operational. And so what I didn't understand is how that notion that entanglement is, regardless of how it's defined mathematically, like the mathematical definitions are targeting a real physical phenomenon as evidenced by Bell inequality violation. How that relates to this idea that I can just change whether a state counts as entangled or not by carving up the Hilbert space differently. So I just wanted a little bit more explanation.
Yeah. And to me, right, that's the key to this physical criterion here, right? I mean, we have this mathematical possibility of making these kinds of definitions. And then the question is what physical criteria? Zanardi said it had to be controllability. There had to be an operational mechanism in the laboratory for where you could build the correlated measurements necessary to extract these kinds of things. For example, in linear quantum optics, you can do this. You have enough control over comparing interferences between different branches of some sort of interferometer that you can make non-local observables. Non-local in one sense, but local in some new observable induced sense of local. So your point is spot on. My claim, right, so even though I don't want to try to say that symmetry does everything, I do want to ask the question, okay, well, what if I say some symmetry is important? Is there any way I can get any of that just from symmetry without going all the way down to the operational level? And I claim you still get meaningful physical results. And that give you I keep using this word again, maybe wrongly, but preferred context. Yeah.
I thought that the most important part is this sentence that you put once in black and then in white.
Yeah.
But then you kind of, now you need it to answer a question.
Yeah.
And local accessibility, we have physics. Local accessibility, we have only local interactions. And when people start to talk about entanglement, it's not entanglement between spin and momentum. It's entanglement between Alice and Bob. Entanglement something here and here. There is no all this algebra, whatever, local accessibility, local interaction. We have only local interaction. So all these things should be based on physics, and based on physics, it's here and here. Entanglement between here and here, not between symmetries, algebras, operators, whatever, between different locations. Sometimes maybe some we have this quantum frame of reference, some subtleties, but basically entanglement between here and here.
So I have two responses. One, you're right. One, you're wrong. Let me try to do both of them. So I, right. So I completely agree, and I get this reaction a lot, and I think a lot of people who think about this get this reaction a lot, right? If your definition of local, if you mean a space-time definition of locality, and you're going to say entanglement is only space-time, that is the only definition, then you are right. And what I am talking about here is I am literally, maybe I should not call it local, maybe I should call it locale, right? Or right? But so what I mean is, right, is I can say I'm going to talk about local. I'm going to define local in terms of I have subsystems, which I can define perhaps still by physics, by controllability, right? This all comes from quantum information theory, where you have these webs of qubits, and so you can define entanglement from a resource perspective. And you can say, well, could I use this kind of entanglement as a resource for quantum computing? And then you say, yes, I can use this kind of entanglement for a resource for quantum computing. So then it's got to have some meaning, right? That's a physical meaning. If I can do an operation that I couldn't do in a classical computer, then I have to have used some kind of coherence. Now, I claim maybe I shouldn't call it entanglement. Maybe I should just say it's distributed coherence, because I truly believe that entanglement is not the resource for quantum information processing. It really is just coherence. It's just the pure states and just the ability to do interference. So I think it could just be we're disagreeing about definitions. But I don't have a better word than local. I don't have a better word than local, and I'm going to stick with it for a while longer.
I agree. You can have entanglement in the same place, which you can use for quantum advantages. I agree.
No, I have two questions. The first one is related to the algebraic approach to quantum mechanics. You can formulate standard quantum mechanics using only algebra, and you can use that approach for quantum field theory and also quantum statistical mechanics. And in that case, you are not so stick to the Hilbert space formalism. So you can speak about notions like this one between algebras, which do not always factorize in a terms of product,
right,
but you still have a meaningful definition of entanglement. So my first question is why not? And the second one is an observation, which is many people is talking nowadays that entanglement is a particular case of contextuality. And there's, yes, some people say that. Wait. I'm just saying what some people say. So, and many people now is blaming contextuality as the resource responsible for the effectiveness of quantum computing. So why not interpreting this relative entanglement in terms of contextuality and trying to find non-contextuality equations for inequalities for this approach?
So I'll answer your second question. So I'll answer your second question first, which is that would be a great idea, and especially then if one could formulate it in such a way where one can make a few-body system, where one can do a novel contextuality test experimentally. Well, then yes, I will be riding a golden chariot to fame and fortune. So I agree. I'll get right on that. No, I mean, I think that's a good idea. I really think that that is a right thing, and I want to understand that better. Your first question is why not generalize this? And some people have generalized this, and you know, in the Barnum and Viola work, and right. So I mean, and Balachandran, and so I mean, people are working on this, and I admit I'm stuck in quantum mechanics. I don't know what to do, right? I'm stuck in quantum mechanics. I'm not, but anyway, but yeah. So I agree that I think there's lots of work to be done there. Yeah.
It's similar to Lev. You want to be not confuse people, no? And that local there may confuse the people in the community because I understand a lot the second part.
Yeah.
Physically, that is meaningful. But locality has to do with local interaction, has to do with Alice being here and Bob being there. Why you want to insist on local? Local is a notion which is related to space.
So I would love to hear a good argument. There is already a literature there, so you have to turn a ship to do this. But let me make a different response, right? So for example, the term separability, I've already used it in at least 3 ways, right? There's separable Hilbert spaces which can be decomposed into finite subspaces. There's the separability when we're talking about differential equations and all that. And then there's separability here where I'm just talking about the separability of tensor product structures. And that's just something we have to deal with. Right? Those are not all the same separabilities. And in every context, you have to be careful which one you're using. So I agree, I am using the word local as an analogy to the space-time locality, because if you have space-time local, then you also have this kind of local too, right? You have this tensor product structure, you have an algebra of observables for this chunk of space-time and an algebra of observables for that chunk of space-time. They commute. If that's your whole system, then they span the whole algebra. So it does encompass your notion, the physics notion of locality, but it's just broader. I once tried to call it speciality, but that didn't make any sense, right? Because it's or specificity or some sort of way, right, to differentiate it from locality.
But this is just accessibility. I mean, that's what you ask.
People freak out. Yeah. People,
I mean,
I had people walk out.
Not argue with, no. I mean, I think you want to be understood by people, not the opposite. No?
Yeah. No, absolutely. You're absolutely right. You're absolutely right. So you said empirical accessibility?
I didn't say empirical accessibility. So the idea that you can access, but not just with your mind, but...
Well, what are you going to call it? What if you are accessing it through symmetry? Like, I can't actually reflect left and right. That's not a physical operation. There is no empirical reverse nature, reverse time. I can't do that operation. Do I still call that an empirical accessibility if I'm building my tensor product structure on a symmetry that I could never implement as a physical experiment?
But this is not the kind of controllable observation.
Well, that's not what he's talking about. That's not what he's talking about, but I'm claiming you can also do this game and you get physics.
Yes, but so you use another...
All right.
Okay.
All right.
I actually had another question. My question was just, I like, you started with a concrete Hamiltonian, then you gave us a very detailed general analysis. So my naive question is, what do you have to say then about your original Hamiltonian, given all the theory that you presented to us?
Yeah. So if you have a maximally superintegrable system, so maximally superintegrable means you don't just have as many conserved quantities as you have degrees of freedom. You have 2n minus 1 conserved quantities. You have an extra n minus 1 conserved quantities to fill out the rest of phase space, right? So now you don't just have your phase space foliated by toroids. All the toruses even like have the same period, right? So you've got a ton of symmetry in there. Well, guess what? that thing, you can break it into subspaces and tensor product in innumerable ways that are self-consistent. You can find multiple sets of complete commuting observables, and as a result, you can define non-local observables in the sense that they're not local with respect to the particles, right? You can come up with correlated multi-particle observables that tell you a lot about the system, right? They can tell you, oh, this is how, if I want to do excitations, but I want to preserve these quantum numbers, and it tells you how the structure of the space then changes under variations of parameters, right? Because you really can then use that to categorize a lot of spectral features. So I would say I don't have the killer application yet, to be perfectly frank. Like, that's the dream, right? The dream is to find something new. The thing is what you can show is that the more of these kinds of things you can do, those systems are amazingly powerful, and we get a lot of intuition from them. And then again, as you lose that, you really can see, oh, now I have 5 particles in one dimension, and the interaction strength is an infinite. I've chunked down to just a few integrals of motion. I can't do much with my space. So.
Okay. I think that we have run out of time, but maybe.
We will discuss on this subject because the subject is the same with next talk.
Thank you, Ian.